Welcome to our introduction to complex numbers. In this video, we'll explore what complex numbers are, how they relate to real numbers, and how they can be used in various mathematical applications. To begin, let's think about the problem that led to the development of complex numbers. What is the square root of -1? If you think about it, no real number, when multiplied by itself, gives -1. Positive numbers squared give positive results, and negative numbers squared also give positive results. To address this mathematical challenge, mathematicians invented a new number called I. We define I as the square root of -1. This means that I squared equals -1. With this new number, I, we can now take square roots of negative numbers. This leads us to complex numbers, which have the form of plus bi, where a and b are real numbers. We call A the real part and b the imaginary part. For example, 3 plus 4, I, is a complex number where 3 is the real part and 4 is the imaginary part. One of the most elegant ways to understand complex numbers is through the complex plane. Unlike real numbers that lie on a single line, complex numbers exist in a two-dimensional plane. The horizontal axis represents the real part, and the vertical axis represents the imaginary part. Let's plot a few complex numbers on this plane. For the complex number 3 plus 4, we move 3 units along the real axis and then 4 units up along the imaginary axis. For the complex number 2 minus 3, we move 2 units along the real axis and then 3 units down along the imaginary axis. And for -2 plus 2i, we move 2 units to the left along the real axis and then 2 units up along the imaginary axis. Now that we understand how to represent complex numbers, let's learn how to perform basic operations with them. First, let's look at addition. When adding complex numbers, we simply add their real parts together and their imaginary parts together. For example, if we add 3 plus 4i to 2 plus 5i, we get 5 plus 9i. Next, let's look at subtraction. Similar to addition, we subtract the real parts and the imaginary parts separately. For example, if we subtract 1 plus 2i from 5 plus 6i, we get 4 plus 4i. Multiplication is slightly more involved. To multiply complex numbers, we use the distributive property, and remember that I squared equals -1. For example, let's multiply 2 plus 3i by 4 plus 5i. First, we distribute. We get 8 plus 10i plus 12i plus 15i squared. Since I squared equals -1, we get 8 plus 10i plus 12i minus 15. Combining like terms, we get -7 plus 22i. For division of complex numbers, we use a technique called rationalization. We multiply both the numerator and denominator by the complex conjugate of the denominator. The complex conjugate of a plus by is a minus by. For example, let's divide 3 plus 2i by 1 plus I. To solve this division, we multiply both the numerator and denominator by the complex conjugate of the denominator, which is 1 minus I. This gives us the fraction 3 plus 2i times 1 minus I divided by 1 plus I times 1 minus I. In the denominator, we get 1 squared minus I squared, which simplifies to 1 plus 1, or 2. For the numerator, we multiply 3 plus 2i by 1 minus I using the technique we just learned for multiplication. This gives us 3 plus 2i minus 3i minus 2i squared, which simplifies to 3 plus 2i minus 3i plus 2, or 5 minus I. So our final answer is 5 minus I, all divided by 2, or 5 over 2 minus I over 2. One important application of complex numbers is in polar form. Any complex number can be represented in the form r times e to the I theta, or equivalently, r times the quantity cosine theta plus I sine theta, where r is the magnitude or absolute value of the complex number, and theta is the angle from the positive x-axis. The polar form makes multiplication and division of complex numbers much simpler. To multiply two complex numbers in polar form, we multiply their magnitudes and add their angles. To divide, we divide their magnitudes and subtract their angles. One of the most beautiful results in mathematics, Euler's formula states that e to the I theta equals cosine theta plus I sine theta. A special case of this formula is when theta equals pi. We get Euler's identity. E to the I pi plus 1 equals 0, which connects 5 fundamental constants in mathematics: 0, 1, pi, e, and I. Complex numbers have numerous applications in various fields of mathematics, physics, engineering, and more. Here are just a few examples. In electrical engineering, complex numbers are used to represent impedance, which combines resistance and reactance. In quantum mechanics, complex numbers are fundamental in describing the wave function of a quantum system. In control systems, complex numbers help analyze system stability. As we conclude our introduction to complex numbers, let's summarize what we've learned. Complex numbers have the form of plus by, where A is the real part and B is the imaginary part. Complex numbers can be added, subtracted, multiplied, and divided using specific rules. Complex numbers can be represented in polar form, which simplifies certain operations. Euler's formula provides a beautiful connection between complex exponentials and trigonometric functions. Complex numbers have important applications across many scientific fields. Thank you for watching this introduction to complex numbers. With these fundamental concepts, you're now equipped to explore more advanced topics involving complex analysis and its applications. Remember that even though they're called imaginary, complex numbers are incredibly useful in solving real-world problems.